Okay, my name is Terry Vasquez. I'm with Dassault Systems. I'm part of the North America CATIA brand organization. I'm a technical pre-sale specialist, and we're going to be covering today, as you can see the topic, CATIA composites, working with carbon fiber in a 3D world. I just kind of want to get a sense for the audience here today. How many of you, first of all, have worked with CATIA? One. All right. So I was invited to the session because the rest of the sales team is in Monaco this week, and they said, "Tag, you're it. You're going to go to Orlando." And after looking at the weather, I think it was a better choice to come to Orlando. It's snowing, and they're all miserable, suffering jet lag. So I get to be here in sunny Orlando and spend some time with the SolidWorks conference. This is my first SolidWorks conference, and quite honestly, I've been incredibly impressed so far with the content, the level of detail in the presentations. Years ago, we used to have what was called, what we still do, CATIA Operators Exchange, and these were the CATIA user conferences. Many years ago, they used to be very technical, very detail-oriented. I made a lot of presentations as far as real training content and getting into the nuts and bolts of the application, workflow processes, how you guys do your business, and giving some assistance there. So unfortunately, some of our conferences have gotten more marketing, vendor related, and so forth. So it's really exciting to come here and see the level of degree of the technicality involved with these sessions. So I'm going to try to make that the same way for you. Now, it's a little bit intimidating coming here to seeing 5,000 people all just rabid about SolidWorks, and I can understand it. Personally, I have about 30 years experience working with CAD systems. I started back in the early 80s working for a defense contractor, and we used whatever we can get our hands on. Calma, Intergraph, AutoCAD, you name it. I've worked on a lot of these systems, CADS 5, and then I fell in love with CATIA in the mid-1980s. Back, we started with version 2, R2, and today we're on the V6 3D Experience platform, so I've been covering this for many years. I've been associated primarily in the aerospace industry, working with accounts such as Boeing for nearly 10 years, as well as some of the automotive customers. So, I learned on a slide rule and a drafting board. That's how I cut my teeth. So I just fell in love with computing and all that it has to offer. It's just very an exciting field, and it continues to be exciting. So, one of my areas of responsibility is working with composites. Now, just from an audience perspective, are any of you working with composites today? Okay, fantastic. So I've worked with the Boeings of the world. I worked with the Magna International for automotive design, working with shipbuilding and exploring the new areas that are available for designing composite structures. So we're going to take you through what CATIA has to offer with this regards. So I want to make this as interactive as possible. Pardon? Yes, I'm fine. No, they were all solved. Number one, the infrastructure here is fantastic. You normally kind of, in the old days, you've probably seen this in the airport, running around with our keel cases, with our big IBM systems and trying to lug those on airplanes. Now everything's done on a key. So let's get started here, okay? We'll see how this works. If it works. Let's do it the old-fashioned way, right? Okay, let's bring it into focus. There it is. Okay, let's see if this works now. Okay, there we go. So composites have been around for a long time, right? I don't know if any of you recognize this. This is a little bit of history from the Ford Motor Company. Back in the 1940s, Henry Ford endeavored on some composites, right? It was known as a soybean car. Now, I'm from the state of Washington, and you know with the latest act of Congress, marijuana is now legal. This is actually known as the hemp car. It was actually manufactured by harvesting some fields of cannabis that were in back of the Ford Motor factory out in Dearborn. But Henry Ford put this together. It was 30% lighter, very durable, right? So, and of course, we know that composites goes back many years. But with the advent of the industrial age, we are now seeing more and more products, especially with now new advanced pan type of fibers in the marketplace, and it's just extensive. We can spend hours just talking about composite structures. Now, what are the advantages of composite structures? I think most of you are aware of most of them, but when compared to metal, the modulus, the stiffness, the tensile strength of the material properties is a lot more excellent. Of course, our processes challenges are there, but as far as what the product delivers in the end is very durable. And here you can see Henry Ford slamming the back of this soybean car to demonstrate the durability. And when you think back, that's happening back in the 40s. So composites have been around quite a bit of times here. So we have seen, and I'm sure you've seen, the recent widespread adoption of composite materials across the marketplace. Probably some of your companies are beginning to explore, well, we want to be a supplier to some of the OEMs. Everyone's trying to get things lighter, more durable, more quicker to market. Down in the left-hand corner there, that's a F-117A. Years ago, I had the opportunity of seeing that at Hill Air Force Base up in Clearfield, Utah, at one of the air shows there. It's a relatively funny-looking aircraft, right? It just kind of, I don't know if I have a laser here or what, but it's all flat surfaces. Everything's controlled by wire, right? All that technology, but it's extremely light, very versatile. But that was one of those early adoptions of composite materials. There's a wind blade, and we're working with some of our customers today to develop composite wind blades, not necessarily carbon fiber, fiberglass, and things of this nature, but very lightweight. Most people are aware of the 777 aircraft and have seen the use of composites in the 777. Here's an example of the 87, where there must have been about 15% of composites within the 777 aircraft. You can see nearly half of the 787 aircraft is now comprised of composite materials. It does have a lot of challenges, but you can see the adoption. And something that people may not be aware of is it's now hitting the apparel industry. And so you can see the type of complex geometry you have in a shoe, trying to mold and form and fit this in order for durability requirements and fatigue resistance and so forth. So there's the adoption there. And of course, there's a golf club. Most of you that are golfers out there probably dream about having a full set of composite carbon fiber clubs and so forth, as well as Trek bikes. And again, some of these components that you see, or some of these smaller parts, may be in your SolidWorks customers today, or you're maybe developing products like this. So there is this widespread adoption. Now, what is the challenge of designing with composites? I kind of found this image, and for those of you that have done composites, I think you can probably relate to this guy right here. Years ago, I worked for a defense contractor, and we were doing some work on the space shuttle program. We were doing a subcontract for Morton Thiokol. Everyone knew Morton Thiokol had problems with their boosters. They were all metallic. They had some joint problems, which eventually led to the Challenger disaster in 1986. How many of you remember where you were at that day? Everyone remember 1986? I was in the delivery room. My son was just born. I went down to the cafeteria to get a cup of coffee, and there was no one around, and some gal comes out, she's just crying. She goes, "The space shuttle blew up." I go, "No, impossible. The space shuttle can't blow up." Well, it did, and went back up to the room with my wife, turned on the TV, and it's one of those hallmarks in our life. And one of the reasons it was a hallmark for me is I worked for this company called Hercules, subcontracting to Morton Thiokol, and we were actually working on composite boosters as a replacement to the metal tubes that Morton Thiokol was developing. And the failure occurred, within one of the joints. After the main bird fired up, everything kind of rocked back and forth. There was ice on the outside of the tubes, and it all ran down into the joint surface, expanded, froze overnight, and then, the hot gases found a path of least resistance, and it blew apart. We had actually, in our composites design with the steel adapter rings, had introduced a capture feature to prevent everything from rocking, which is to prevent the hot gases from leaking out. There's a Rogers Commission report out there. I think it's still on the internet. You can find it. But I remember working on this program as a liaison engineering for the filament wound tubes, and the extensive amount of carbon information that we had to capture. Why? Because it was new to the industry. We were filament winding 12-foot diameter tubes, 32 feet long, with the joint thickness about 1.6 inches thick. And I used to do process proofing. Anyone ever do process proofing, checking out a new process? We sat there in our chairs as engineering, watching this thing be wound for 20 days, 3 shifts, 24/7, until it was finally wound. And we were capturing data. Our M&IRs, one of them literally looked like that, a stack of paper with all the shop floor mechanics recording everything, compaction, toe values, resin content values, and trying to get all of this information into a system so we can go back and do statistical process control. Why? Because it's a new program. No one had ever done anything of this magnitude before. But there was a lot of data to manage in that. And how did we do it? Oh my gosh. Doing schematics by hand using CADM dittos to, draw out the schematics, broad goods and termination points and, stacks of drawing. And of course, what happens when you have a lot of drawings, you have a lot of change, right? Anytime you introduce an engineering change order, $5,000 right down the tube. We had drawings that were revision AC, AM, constantly doing drawing updates, a lot of changes to manage. It was very difficult to control. And then we had NASA sitting over our backs as our customer, saying, and Martin Thiokol, and you're going to do it this way, and blah, blah, blah. All of our systems were disconnected, right? We had to push data from one system to another. I had a bunch of data in Lotus 1.2 spreadsheet, and some guys I had were working in Patran and Nastran, and, we had all kinds of systems everywhere, and they were all disconnected. So there was always the opportunity to introduce error as you try to push data back and forth. Very difficult. Then we had a real problem with what we called interdepartmental collaboration. Was anybody really talking to anybody? And when you had the manufacturing facility up in Clearfield, it was 40 miles north of the Magna facilities down on the Oquirrh Mountains, things were always slipping through the cracks. And I think the best thing we had was Wang word processors and prof systems to communicate with, or you'd wait for the mailer to come in your inbox right a few days later, waiting for some analysis so you can disposition a DER, a disposition record against that. And, it was just a mess. No collaboration. Everything's busted apart. The amount of time, to get that change in work into production. And many of you, I'm looking across the aisle and I see a little bit of gray hair here and there, but you probably all remember the days what we called cost plus. Do you all remember that? Where you had government contracts? Yeah, you're laughing back there. You had award incentive dates that if you meet these targets, you're going to get paid extra. So there was always a management reserve, a cash reserve for the manufacturers to meet these target dates. Now we're all under fixed cost contracts and so forth, so all of that free money has gone away. The one nice thing about the free money was that's where cell phone technology was developed. That's where a lot of the technologies that we use today were actually investments made by government funded and contracts. And we actually invented a lot of this stuff with these programs. So there was a lot of fallout, a positive fallout that came through that. And of course, you all know that data is usually outdated. Who has the latest model? Who has the latest data? Gosh, anybody's guess, right? And if you ever had to pull together a drawing package, you used to go get the drawing, right? Get it out of microfiche or, somewhere, and then you'd have to go and get the stack of outstanding engineering changes, and then you'd have to sit there and recreate the scenario, all manually, all by hand. There was no digitized data per se to really go back and validate the design. So, and so you can imagine when you're doing lamina and laminate, ply by ply, splice by splice, dart by dart, trying to build up a product using composites, it can be very expensive, cost prohibitive. That's why a lot of customers don't do this, right? They just think, well, I just can't afford to do this. The material's expensive, the skills, the analytical skills to acquire in order to solve a lot of the complex problems, they're not available, so hopefully I'm painting this picture, looks simplistic when you first start, but those of you that have been in the industry know there's a lot of pain associated with trying to go through this course here. So here we are at a SolidWorks conference, right? And so what is my message to you about CATIA composites? And really the message is that we're here to complement a lot of the smaller design shop installations. And one of the best examples that we have today, I'm sure all familiar with the Terrafugia, which is the transition street legal airplane that was developed. Now this product was developed using SolidWorks for the core mechanical design and the systems development applications, okay? But they didn't have anything to do with apply modeling. They needed some application to do that. So they added on CATIA composites to do the design, the fiber draping simulation, and the analysis, integrated analysis actually coming out of CATIA in order to solve the ply problems. So this is actually a real good story. So what I'd like to show for you real quick, it's going to take about 4 minutes. So I want to run an AVI for you that kind of gives you just a real quick look at what composites is. And oh, he killed my thing here. Let's see if I can get this on the right screen. I'm going to let this play and go ahead and enjoy this. Well, hopefully you were able to comprehend some of that. But that was just kind of a high-level view. So the composites application portfolio in CATIA is not another third-party application. It is, in fact, CATIA. Okay? And what we've done is we've developed the workbench in order to cover the entire process flow from preliminary design all the way down to fabrication. And the way that the workbenches have been designed in CATIA is basically to start with the preliminary design. And here in preliminary design, we capture a lot of the early analysis and manufacturing inputs. This is very important. And here I have all this data in the historical world. It's all separate systems and so forth. Here, everything is encapsulated in the preliminary design and detailed design world. And once I've captured that information, I can then either use integrated CATIA tools, integrated analysis tools, to do some more fundamental type of analysis. And really, it's not really trivial. You know, we can do some buckling analysis, some thermal analysis, and so forth directly inside of CATIA with what is called the Al-Fini solver. Or if you need some more advanced capability in analysis, we can link that information seamlessly from the CATIA workbench into Abacus. Now, Abacus is our Simulia brand. Have any of you been back to the Dassault booth that's hiding back in the corner in the pavilion down there? So if you kind of go through there, you can see a lot of the different brands. When I first hired into Dassault Systems, all we had was really CATIA and this little PDM system called CDM, CATIA Data Management Tool. And then we grew out to something called Innovia, which is our large-scale enterprise product data management. We had a need for some manufacturing stuff, so we acquired Deneb Robotics, which became our Delmia solutions. And then we acquired Abacus. We need something on the market that could contend with the Nastrans of the world, the Patrans and so forth, and that's what Abacus brings to the table. We branded it called Simulia, and then the list goes on, 3D Via, Exlead, NetVibes, et cetera, et cetera. So, but today you can send your layup files directly from CATIA, the composite layup files, into the Abacus world, composite modeler for Abacus, or some Abacus explicit to do some more of the advanced analysis for experts. So once you're done with that, you can come back and continue the workflow process and do what we call manufacturing preparation. Okay, and this is where you're adding on material excess, you're swapping it to the actual tool, the mold tool, because you have an engineering tool, right? Just like sheet metal, right? You're going to have a form block. That form block's going to have a surface spring back condition to it, where you're going to have some of the same type of semantics with composite parts. So we have a manufacturing preparation to capture that knowledge, and to allow you to do that, then you finally have the manufacturing export. And we have a very robust partnership with, maybe you've recognized some of the vendors out there, Ingersoll, Taurus, and so forth. They've been around for many years, and we have some very rich and very mature interfaces. There's something we call CATIA application architecture, and that allows a lot of our gold partners to integrate their software directly into the CATIA environment, just like you have with SolidWorks partners today. So we have that with a lot of our equipment manufacturers. So this just kind of gives you, this is the only eye chart I'm going to show you, by the way. I know sometimes we throw up a bunch of information, but I've kind of streamed this down a little bit. I just wanted to mention a word about best practices, and I'm sure best practices in CATIA are very similar to what you have as best practices in SolidWorks, right? For example, all of the CPD is actually our term for our composite part design. Okay, so when you see CPD, that's what it refers to. Since it is CATIA, we build right off of the CATIA geometry, the wireframe and the surfaces that are sitting in your model today. So if you have junk going in, you're certainly going to get junk coming out, right? That's why I kind of threw up the metaphor there, trying to fit that square, block into the round hole. I was at a customer a couple months ago, and he's a user, and we're sitting having some dialogue about what he needs, and he goes, well, I can break CATIA. I go, oh, really? He goes, yeah, I can break it. I can do this, and I can break it, real easy. I go, yeah, and I said, well, I can probably, drive my car down the freeway and probably throw it into reverse if I wanted to also. It's not something I'm going to do, right? So that's why we have best practices. I'm sure your seasoned users, that you're going to have conditions that you have to manage beforehand. Things such as the internal cell tangency of your surfaces. We have multi-cell surfaces, so you want to make sure that the tangent continuity is well aligned inside of them. The surface offsets, you want to be able to, if you know that composite ply laminate is going to build up a certain distance, you're going to want to make sure that you can offset it in both directions without getting what we call degenerate elements. The surface boundary, you got to be able to extrapolate that out, right? Because you're going to have manufacturing tool excess that you have to account for. So these are just some of the things that, I as an engineer recommend when I go to accounts and say, let's get first things first. Get this straight, and life's going to be a lot more easier. We have some very powerful surface simplification and healing tools directly in CATIA. And this is to check a lot of the tangent conditions. I'm sure if you've gotten a lot of files in from other CAD sources, IGES, you get surfaces that are stepped in, and sometimes you zoom up real close to the boundaries, you're going to see gaps and things. You really want to heal these. You really want to take care of these. And so that's what I'm talking about right here. Okay? So the first thing you start with when you come into CATIA Composites is you want to start with a catalog of material properties. Right? So we talked earlier about having sources of data spread all across the enterprise. We can actually take that information and capture them in the CATIA catalog of materials here. Now, what does this catalog have? It's just not a name saying carbon, 0.0395, right? If you look at some of the panels in here, for example, I have one for analysis. It has all of the analysis properties input, Poisson's ratio, transverse ratios, and so forth, all of the strength, modulus factors. All of these information will be carried with the CATIA model as it traverses across the process, and it will be used by the different algorithms of our modelers and our soliders directly in there. So here you have one for manufacturing. I have some things like cured thickness, uncured thickness, material roll width. Why is material roll width important? Well, if you have, a wind blade, and you have material that's only so long, and you begin to lay that out, well, you may have to splice it. Our system will tell you that it needs to be spliced based upon that material property that's put in the system. We even have cost. So if someone wants to go ahead and analyze or do a trade study on their product, they can, well, how much is this thing going to cost me? And they can extract that information directly from what was put in. And then we have drafting standards for how do you want to cross-hatch it and so forth to do the laminate. And everything is stored within what we call a geometric set inside the CATIA model. So all these properties are going to be inherited and travel with this part. So how do you design a composite part in CATIA? It's really simple. You start out with a simple surface, some boundary, right? This is what my net engineering boundary is going to be. And you select the material that you want. Then you define the manufacturing process. In this form right here, we're going to talk about things, what is the draping direction? And where is my rosette going to be placed on the composite part so I know what my fiber angle orientations are referenced from. So all that information is put in this panel. We also have some options to specify what the process is. So I have, for example, a hand layup process, tape laying, or automatic fiber placement. And by selecting these options, it'll connect you to, if you have the vendor app, the right interface for specifying how the fiber deposit is going to take place. So all of that is done right up front. Then we have the specifying the contour and the attributes. You can have multiple catalogs of one part, right? Because your part may have some substrate material. You may have some S2 glass. You may have some honeycomb in there. Then you may have some additional broad goods or pre-preg material that rests on top of that. And you specify all that right within the interface. Once that's done, you're pretty much a compute button away from getting all this information. It stores it all within the cap part, the ply, the sequence, the group, and all these attributes that are associated with it. And you can see that I just kind of extracted some information, just what does a cross-section look like. Now, when I think about what I had to do years ago in order to get this level of information, I would spend 40 to 80 hours a week just to get something simple produced on vellum or, on paper. So all that is now within the systematic process. We also have another technique we call solid slicing. So imagine you have a sheet metal frame or something, and it's metallic, right, aluminum something, and you want to go ahead and convert that to composites. We have a technique we call solid slicing. And you can see I have a dedicated workbench for this type of operation. And a lot of these things that you're seeing right now have been requirements that have come to us from our customers. They're saying, what if I can do it this way? As a baseline, right, I don't want to have to start from scratch. I want to start with an existing structure. Maybe I'm doing MRO work, maintenance, repair, and overhaul, and I want to replace a component with a composite component. And here's my solid. It's a dumb solid, but I want to be able to convert it into a composite laminate structure. Well, we basically define what we call the zones, and each one of these zones is going to be comprised, say, of what is my laminate thickness? How many plies am I going to have in here? Maybe I'll have a transition zone in the middle where I need to do the drop-offs and finally get down to a thin material. And then the system automatically slices that and gives you kind of a rough order magnitude preliminary design. Okay, so we're still talking about kind of a preliminary design approach of how do I quickly generate a representation. So that's just one of the methodologies that we have. Now there's another methodology that we introduced in our release 18 version of the product, and it's called the grid-based design. Now this is driven by customers such as Boeing that have large wing structures, right? And if you look at a wing, it's comprised of a bunch of some ribs and spars running through it. And the way that analysis worked, they kind of worked in this brick model. And this is how they do their laminate studies. And so here's my box of chocolates. So I kind of came up with this last year. And as you can see, there's some symmetry to this, right? And the symmetry is really found by breaking it up into this grid pattern. And this is the same, say, with aircraft structures and in many other structures. You have some logical breakdown and decomposition of the product where there's going to be some commonality, okay? So we're able to break it up this way. So if you look in the contents there, you know, we have different types of chocolates, if you will, and each of them have some sort of quality to them. So we can find what that commonality is with this approach. And that makes it a very easy way. And I can also integrate this with an Excel spreadsheet, by the way, so I can quickly import and export design tables in order to satisfy this requirement. And so what does it look like within CATIA? We start with some assembly constraints. We call this assembly and design context. And so I have some frame stations, some other lines there to define that. Now I define what I call a grid panel. That grid panel is going to have manufacturing specifications in it. I'm going to be able to tell, as a designer, how I want the drop-offs to go, what the slope rates of those drop-offs are with relation to some of my key reference planes within this structure. Once that's been captured, I can go ahead and define what the laminate looks like. So within each one of those cells, I know I'm going to have either a stacking sequence or I'm going to have some sort of thickness law. And this is still all kind of a preliminary design. And I can kick out, an Excel spreadsheet there, and I can pass that back and forth between my analyst. Now, I worked with an analytical group for many years, and this is how we used to do their designs, just this way. It's a very, very nice and elegant way of doing it. Once I do that, I can do something we call a virtual stacking. What CATIA will do is it will automatically query what my grid panel contents are, and it will propose a symmetrically balanced laminate stacking based upon all the common elements in there. So you can see the highlighted field says, well, this pattern right here is common. So that now becomes a sequence or a ply stack. So that type of logic is very quick, very fast, and saves an incredible amount of time. And then finally, I can generate the plies. And in the figure in the lower right-hand corner, you can see I can take the drop-offs, and I can move those drop-offs around. Just to manage those drop-offs, if you were to have to do that manually, it would take hours, if not days, to do. And we can do it in an automated fashion. I can actually specify what my drop-off patterns are like based upon particular rules that I apply to the system. And then I can get the solid from that. So what do we get? We get a rich composites model. All the information is stored directly in the CATIA CAT part. I have ply table information where I can export all of that ply data into an Excel spreadsheet, or I can incorporate it back into my drawing. And it's all linked. It's all associative. So if I do an update on one end, relationally, it'll update on the other end. I can do section cuts. And just to do this type of cartooning, right, for shop floor mechanics and so forth, it is a very quick way of doing it. I can do some core sampling, engineering drawings, get some numerical analysis, some wetted surface area for all the plies. We now have some new applications where we can do center of gravity and weight distribution with respect to the composite material. And I can finally export it, whether into an XML, IGES, STEP, or what we call the explicit AP 242. Anyone familiar with, you're all familiar with STEP, I'm pretty sure. You're all familiar with some of the nuances of STEP, the new protocols that are coming out, like AP 203 Edition 2. AP 242 with an explicit definition. These are beginning to capture, through STEP, model-based definition. Geometric dimension and tolerancing is now supported by that, as well as a composite working schema. So applied definitions are now included, and I'll show you that in a couple slides here. Now we can also take this composite geometry directly in CATIA and solve it, and it's all associative. So if I make any change to the applied definition in the CPD workbench, that will be reflected in my analysis, and I just have to recompute and resolve the analysis. So that's all integrated directly inside CATIA. Now, we have the ability to take that CATIA layup file, as I said earlier, and then transfer it using what we call our composite link technology and directly into Simulia. I can also export this layup file into ANSYS or Nastran, or into a neutral format that reads a layup file. A layup file is basically a patented technology owned by Dassault Systems for a common neutral language format of composite definition. So we can do that in this way. So this kind of completes this scope of it. So let's look to manufacturing real quick. So I don't know how many of these processes you're familiar with or actually put your hands on. I've put my hands on about half a dozen of these, but these are the challenges that our customers are facing today, right? Okay, so you give me these great tools, how do I actually produce and manufacture? Laminate it, fabricate it, and so forth. So we're addressing a lot of these today in composites. As Bernard Charles said early in the opening presentation, we were kind of laughing about R&D budget, right? Dassault Systems has the largest investment capital than any of our competitors by a long shot, and we're continuing to invest and make advances in this. And as you can see, I hired in, I think there was maybe about, in 92, 500-600 employees. Now we're up to 10,000. So it's very gratifying to be part of an organic ecosystem. So we have a dedicated manufacturing preparation workbench, okay? And this allows us to prepare the document for doing manufacturing operations, like skin swapping to the tool surface, material excess, and so forth. And then doing what we call producibility analysis, flattening, and things of this nature. And the way that our workbenches work, they're kind of sequential, kind of left to right. So after you've got your training, you can pretty much follow the process. And then we have some other common toolbars. So the way that the workflow works is you basically come out with this manufacturing representation. I'll talk about that in a second. Then you do your skin swapping, get your material excess, and run your producibility analysis. Basically, producibility is how do I deposit the fiber on the mold tooling? And where is it going to wrinkle? Where is it going to buckle? Where do I need to dart it? Where do I need to splice it? We have tools that will actually predict that for you, which is an incredible time savings. I've done repair work on the shop floor years ago, and I can't tell you, anytime I had to scrap material because it buckled or wrinkled, we get in trouble. I mean, a piece of pre-preg is expensive in the time to put it. And also the exactness of it, right? Because when you put in composite material, it has to follow an analytical process, right? I have a load path. I can't just slap that material in any way I want. I got to be able to follow some characteristics of that. And then again, to get the flat pattern. So the first thing we do is we create another CAD part, okay? On the left is my engineering definition. On the right-hand side, I have what we call a manufacturing definition. So the workbench allows me to create this symbiont of the engineering model, and they're associatively linked. So this allows me to get my tooling folks and my manufacturing folks started early as soon as I feel that my design is mature enough. Why? Because composite tooling or Invar tooling or any type of tooling is very expensive. And sometimes you need that long lead item. I got to go get some material. I remember on the space shuttle, we had some D6AC steel rings were being fabricated out of Southern California. The lead item of those things was about 8 months, just to get the rough cut. I think it was out of Votal machining, and that's a long lead time. And if you make a mistake, you got to make a change. Guess what? That's not a cheap mistake. So getting manufacturing started, getting them in their process early is very important. So that's why we created this additional model. And you can see in the highlighted areas there, the one on the left says engineering, the one on the right says manufacturing. And these are keep synced together. So here's an example of our draping simulation. So what are you looking there on the left-hand side is how the fabric is being deposited on the mold tooling. Now, the blue area represents what we call no shear areas, okay? The warp and weft direction of the material is going on the mold tooling per specification. Now, the yellow area represents I've exceeded what we call the worn angle. Now, these are all being consumed right now from that material properties catalog that's with that cat part. And so our solvers are recognizing them. And of course, the red area says that we hit the limit angle and my material is now beginning to shear, it's beginning to warp, it's beginning to buckle. It's out of spec. Either I got to dart it or I got to do something. Now, if you also look at the flat pattern, that is not a realistic flat pattern. I asked my wife, she does alterations, and she said, yep, that would never work. You got to dart it, right? So after running the producibility analysis, we now come out with some propositions for curve and line darts. We can read those from a catalog, and then we know where to cut that ply piece in order to make sure that it wraps around the mold tooling. Now, would you rather do it in a simulation environment or go out to the shop floor where you're going to have to scrap material possibly? And not just one ply, but probably multiple plies. You may get to a point where that stacking gets a little bit thick and all of a sudden you have a problem, right? So that's what our draping simulation does. Another example I wanted to show you here is what we call the seed point and curve management. So on the left-hand side there, if you look in the lower left-hand corner, you see a blue line and a red line. That's the warp and weft direction of this unidirectional fiber that's going on this tool. And you can see where that's the starting point where manufacturing is going to put it on the mold tooling first. As he begins to wrap it down that channel, you'll see that it begins to turn yellow and then ultimately red, which means we have a problem there, right? It's going to lock over there. The other thing you can't see very well, but the fabric is actually going parallel to the x-axis, okay? Now that's fine for the initial couple inches, but as soon as you go around the S-curve there, I actually want that fiber to follow that direction, okay? And if you look at the flat pattern, that also is not realistic. So this part would essentially, you'd be unable to really laminate that. So using what we call the seed point and a seed curve control, I'm actually going to select a point on the center line of that channel where I want manufacturing to start their deposit and then begin to feather it out. And I also want the fiber direction to follow that curve because that's the curve of my load path. That's where analysis says I got to go. And so what you end up with is this type of simulation here and a more reasonable flat pattern. And what you can't see, I know it's real small, but right there in the center of that plane is where the warp and weft direction is going. So then I can kick this out to a flat pattern, export it out to a DXF format, read it into some nesting software, and I'm off and running, okay? So these are some of the downstream manufacturing operations that we have. We can do what we call composite ply books for shop floor. We also, I don't have an image of this, but we can also use 3D via in order to build the stacking on that. I know you can't see the center black screen, but that's a draft site, and I've actually imported one of the flat patterns into draft site. There's no reason to bring it back into CATIA, right, if I'm going to export it. So, and then we have some material deposit relationships with some of our customers. I want to show you just a couple of those. One is from Majestic Systems, and what we do here is something we call True Nest for nesting, all of those plies, and also what we call True Laser. And that's for laser projection systems in order to get this into the mold. This interface sits directly inside CATIA today. So by buying this add-on, you can have a seamless process like that. Another tool that we have is one for doing PAM RTM simulation. For how do I do my resin injection processes? How do I determine what the permeability of my material is, the pressure of the resin, the viscosity of the resin, and simulating how it will flow throughout my entire part. And that is also integrated inside CATIA. And then we also have some relationships with Coriolis and Taurus and others where we can actually do directly inside CATIA. And for Coriolis, we have a product called Cat Fiber where we can actually do the robotic simulation of the tape laying process using the composite workbench as well. Okay? And just one last point I wanted to highlight here is something we call LOTAR. It's the long-term archiving requirements that are specified wherever you have kind of like a type certification product, where you're going to have to manage the digital representation of that product over the life of the product, right? So I kind of think of the 747, which was developed back in the 60s. Well, they're still in service today. So if you have crash investigation for a 47, you got to be able to bring the entire drawing package on site within 48 hours according to the FAA. So how are we going to do that in the digital world, right? Where you have new systems, constantly evolving systems, data models are advancing. So STEP has come out with these application protocols in order to define what the work methods are in order to not only store, archive, but to retrieve that information for such events as that. And so as far as I know, CATIA is the only one that's been able to implement the STEP AP203 Edition 2 that supports the composite schema, data schema, and support that working model. And that's very important for the data exchange, interoperability. So for example, if a customer has, an OEM has a V6, and they have composites on V6, they can go in and export it using this format and then read it back in to V5 along with the entire composite definition. So these are some of the important aspects. So that didn't take very long. That's really all I wanted to share with you. Since you're not really CATIA users, I kind of wanted to keep it a little bit high level. But that's what we have for composites. Any questions at all? I know we have a little bit more time here. Yes?
Are there tools
For the molding, actually creating the molds. So for that, inside CATIA, when I do the composite definition, I talked about that skin swapping. We have surface generation tools that will read that composite material because many times you may have offsets and you have to provide tooling and molds for those different offsets. I can actually extract a surface directly from that composite definition and use that for that mold tooling design. And because it's CATIA, that mold tooling will work with the mold and die workbench in CATIA. Or you can export it as a step file. So it's still all CATIA. That's a good question. You had a question?
CATIA and SolidWorks being under the same umbrella, do you see a file format which they look at a little bit easier? Because it seems like it's difficult to get CATIA into SolidWorks and take SolidWorks and CATIA and go through the different steps.
Yeah, I understand. A little. So the question, the observation is, I don't know if you could hear back there, but you have CATIA, it's a CAT part format, CAT product format, CAT drawing format, CAT analysis, CAT process. Then you have your SolidWorks file format, and oftentimes they don't exchange very well, do they? Well, I know today in our more recent versions of CATIA, you can read in a SolidWorks part very easily. And so the earlier example I showed with Terrafugia, I believe that's how they did it. They were able to read the SolidWorks part into CATIA and then add the composite definition on top of that. As far as going from CATIA to SolidWorks, I don't think that exists other than step or IGES. I can look that up, but as far as I know, that doesn't exist today. Unless someone else has done it. Has anyone written some code to do it? No, it doesn't exist today. Yes?
So, composites having anisotropic properties depending on the geometry that you set up. Obviously, you can calculate some parameters as far as the product's inertia, or the component, etc. Is there an interface for bringing those into 6-degree freedom analysis package, or calculate or visual visibility analysis for aerodynamic applications?
Yes, absolutely. So the question is, can we actually take that information with all the analysis background, moments of inertia and so forth, and bring it into a more advanced expert system, right? So I mentioned that this CAT part is going to house all of that information inside of it. today. So we have a product called Composite Link that allow me to export really a layup file, which I can read seamlessly into Abacus, and the Abacus composites modeler for Abacus will read that natively in. I can also export a Nastran BDF file, and it will carry all that properties information with it. I can also export, an ANSYS file as well as XML data. But all the material properties that I had specified in the material catalog will go with it. And so they'll be reconsumed. So you don't have to redefine them.
And how does the database handle digital materials? Digital new stuff, additive manufacturing processes allow you to sort of mix up binders and things like that.
Yeah, that's a good question. So the question is, how do we do additional type of material catalogs, different types of properties? How do I answer that? I know the problem very well. First of all, the material catalogs that we have in CATIA today are for reference only. As you all know, with composite material, we fall under the classification of ITAR, right? So there's not a whole lot of people that are willing to share with each other because it's listed on the CDRL's list, and you just can't send it out. When I worked in the industry, we would have to certify our own material laminate properties, right? So the company I worked for, actually, we had a fiber line. So we produced, AS4 fiber, IM7 fiber, so that was back in the 80s. So we would actually have our own resin systems that we would develop. We do our own coupon testing. I was responsible for doing project management of getting this testing done for the Space Shuttle Filament Wound program. And we had probably 36 different types of tests. Isocompescu shear samples, double lap shear, tensile tests where you have 1.5 million kips. Tensile, these are pretty tough materials. Then we get those allowables. And so those allowables would become our baseline. And then we would take those allowables and input them into a system like this. Now, not the CATIA system at the time, but whether we were doing stuff with Nastran or Patran or whatever, we would feed the system with all of those allowables. So every customer will more than likely have their own set of allowables for their own coupon testing and how they, because when you're doing filament winding, for example, right, it's based upon what your resin content is, how rich you're going to make it, what kind of fiber you're going to use, what type of fiber. If you look at, Hexcel Corporation, they have catalogs of different type of fiber, and you can impregnate that with any resin you want, any temperature you want, thermoset values or whatever. So we are working with some academia institutions as consulting firms in order to provide services to some of our customers. We have one of our automotive customers that wants to do a high rate PAM-RTM process. So say, for example, if you have a B pillar on an automobile, right, that's a high production rate. You're probably producing hundreds or thousands a month, right, of B pillars. Can you do that with composites today? No. You just can't. So they've given us some requirements that say we want these systems to be able to punch that thing out in 1 minute. And so we're working with companies like ESI and others to say, how do we get this rapid production with the quality on the other end? And a lot of it is how the processes are putting together that materials matrix and making sure that they have a process that they can certify and reproduce accurately. It's a tough challenge. Yeah, and then swap it out. The CATIA materials that are inside that tree, that product tree of the CAT part, they're actually linked to the catalog. So if I update the catalog, I can recompute my composite part. Now I got to be careful because I have other things like cured thickness. So right, if all of a sudden I increase the thickness, even by a few mils, I've eaten to some tolerance, right? So I got to kind of go back and figure out how am I going to do this. So there's a lot of things that are impacted. The nice thing is that it's all relationally linked. In our new 3D experience platform, which is built on V6, all the materials will be in the database. Again, another problem, right? Not only do we have parts copied across the enterprise, we have material databases all over the place. Who has the latest one, right?
So these are some of the new additive manufacturing technologies that are coming where you basically configure, like you would make binders, right? Because they're applied digitally over the surface at very, very, very fine refinements. So through that, because you can
Yeah.
So I'm just trying to see how those relate to not handling.
Let me kind of take you back to an illustration here on the grid.
This is all new stuff.
Right, I understand. I don't know if I have, obviously I don't have all the answers to all of this stuff, but I just want to get back to this one picture. I went through a lot of slides, didn't I? Okay. So right here, if you look at the virtual stacking information, right, what I'm reading an incredible amount of information in there. And so I can swap that material out if I wanted to. So I can have multiple materials inside this part, and I can begin to swap them out. Now, it's going to impact a lot of different things. So I can have multiple materials in my part. Like I said earlier, I can have one ply is going to be substrate for glass, sacrificial layer, if you will. I could maybe have another layer. I can probably stick in like a polymer for insulation, right? Thermal barrier. I can have a core in there and some overwrap materials. So I can actually mix and match materials inside the same cat part. And CATIA will compute, for example, mass properties. It will know that I have a weight distribution based upon the different properties that are in there. So we'll compute that. Does that kind of answer it? Yeah, it's a deep conversation. Yeah. Any questions? Any other questions? Okay, we are in the pavilion, back in the little ice cave, I call it. We're in front of the SolidWorks people, and everyone just keeps, but I have CATIA up and running on my laptop, so if you want to see a more detailed explanation of anything. Well, thank you for coming. Appreciate your attention.